Let me do this again, see if I can turn. See if that audio will come through that way now.
Your goals for learning are to describe the general functions of the immune system, to describe the key characteristics of the common types of pathogens that can attack our bodies, to name the 3 lines of defense and outline
Loud enough.
to distinguish between innate and adaptive immunity based on 4 key characteristics, to understand the definitions of antigen and antibody, to distinguish between humoral and cell-mediated immunity and the location of the pathogens they target. Here's what you need to know.
All right, well maybe what I'll do is I will talk over it while you see it playing there. That might be a way to work it.
To see definitions of terms,
Let me do
use
this.
the bold red words.
Turn this one on. And that one off. I'll show you another page. Okay, so some of the things that we were discussing last time, you see coming up on the screen now, right? So we were talking about the immune system is destroying pathogens, and the pathogens, remember, are going to be the disease-causing agents, right? So it could be bacteria, viruses, and things like that. But a few of the other things that the immune system is going to do is it's actually going to detect and kill abnormal cells, such as cancerous cells. And cancerous cells are basically our own cells of different types that have lost the ability to know when they're supposed to reproduce and when they're just supposed to be in interphase of doing the normal day-to-day activities. And so they're just reproducing out of control. And so part of your immune system will actually be working to get rid of cancerous cells or even precancerous cells. And then a third function is to remove dead cells and cellular debris, a bit like we were talking about when we were talking about things like the spleen, etc. All right, so let me show you some of their funny analogies, right? So here's their guy showing them, all the different pathogens that they would need to be aware of. So we had mentioned these before, right? So parasites like parasitic worms, which are going to be the biggest ones, and these are in fact big enough you might be able to see them with the naked eye. Then there's things like fungi and protozoa, but the bacteria and the viruses are the most common. And the viruses are the smallest of all of them because the viruses actually have to go inside your own cells. So in essence, they hijack your own cells and use your own cell machinery to reproduce themselves and then spread out from there. So we had talked about that, yeah. So here's the part where I was talking about, like the 3 lines of defense. And I think it does a nice job of making the analogy, like we were talking about, between the outer defenses and the inner defenses. And so, for instance, with the castle or whatever, if we're talking about like a medieval battle or war, we're talking about the walls and the moat. And if we're talking about the body, then in essence, like we were talking about last time, we're talking about things like the skin, we're talking about the mucous membrane, we talked about the gastric juice and things like that, things that are at the surface of our body that are trying to prevent these pathogens from actually entering our body. Okay? So then from there, we would have our first layer of defense, first line of defense is going to be then non-specific and external, trying to keep things from getting inside. So the second line of defense is going to be internal. So if they breach the outer barriers and they get inside, we've got to try to take care of them. And what's going to happen there is we're going to have internal cells that are, again, non-specific. So when we say non-specific, what they're going to be doing is they're going to be on patrol looking for things that don't belong there. And it doesn't matter exactly what it is. If it's not recognizable as self, if it looks like something that's foreign, they'll try to get rid of it. And these are usually going to be things like our phagocytes, etc., right? We talked about like monocytes and things like that. because it's internal and it's non-specific. Our third line of defense is also going to be internal, but it's going to be specific. And in this case, we're talking about the lymphocytes. And we mentioned a little bit about the lymphocytes last time. We mentioned the fact that there are two different types, even though they look very similar. There are T cells and B cells. And so what do the T and the B remind us of when we were talking about last time? Yeah, bone. And then so it's talking about where they mature, where they go through boot camp. And the B cells are maturing the bone, and the T cells are maturing the thymus, right? That organ that sits right superior to the heart, and it's much larger, much more important than actually when you're young, and then as you get older, its function goes down. This part's really funny here. So you see this invader kind of coming up to the border there, and in essence, the guard there is like predator foe. The guy goes, oh, whoa, and then you get stabbed and he dies off in his way. But in essence, right? So this is representing that innate immunity that is helping to protect us externally so that things don't breach our outer barriers. And then if it gets past that, then we still have innate or non-specific immunity that can continue to protect us inside. But when we get to the specific or the adaptive immunity, this one, we said the specific nature of it means that it cares exactly what is attacking you. And so it's directed against a very particular identified enemy, whether this is a virus or whether it is a bacterium, and what particular virus it might be. And so the different cells of the adaptive or the specific immune system have to be able to go and identify these different cell types, and then they have to be able to see exactly what it is. And we said that the adaptive cells are going to be our T and our B lymphocytes, like you see here. Now, the interesting things about these is, again, I think they do a good job with this analogy. T and B lymphocytes, we said they look pretty much the same, but in some way they've got to be different, right? They have different names, they come from different areas. They probably protect us from these specific pathogens in different ways. And notice that the T cell right here has a spear and a shield, and as you can imagine, like a foot soldier, the T cells are going to have to do hand-to-hand combat. So basically, in order to identify and combat a specific pathogen, those T cells will go up and they will bind with the foreign pathogen. Right? The foreign pathogen is going to have those foreign antigens on its cell surface, so it's going to bind to that. And while it's hooked up to that foreign cell, then it's going to like secrete chemicals on it or stuff like that, which is going to kill off that cell. But it has to go and engage the enemy. It actually has to attach to it and do this hand-to-hand combat. Okay? That's the T cells. The B cells are more like archers, or in more modern times you might say people that are kind of manning missiles and have their finger on the button or something like that, right? So they're also part of the defenses, but as with archers or people that man missiles, they don't have to be right there in the battle, in the thick of things, in order to have their effect on the enemy. And so oftentimes then our B cells, what they're going to do is they'll be located in places like our lymph nodes, like we talked about before, and when they become activated, what they're going to do is they will, in this case, they're going to put out arrows, right? And those arrows are going to kill off invaders. Well, the arrows that a B cell will put out are in fact antibodies. So we talked about antibodies before. They're proteins that are floating around in the plasma. So those proteins that we learned about before, called antibodies, are produced by B lymphocytes. So the B lymphocyte can sit there nice and safe in a lymph node or something like that, and when it gets exposed to a pathogen that it recognizes and that it can have an effect on, then it starts pumping out all these antibodies. And the antibodies go into the lymph, they go into the plasma, and they can circulate around. And anywhere where those antibodies find a cell that has a matching antigen, they'll bind with it, just like we talked about with the blood types, right? So we said that when the antibody matches with a particular antigen, it's going to form a bond with it, it's going to link with it, and it almost acts a little bit like molecular handcuffs, right? It's going to hold on to all these cells, and maybe then different macrophages or phagocytes will come by and get rid of those cells that have kind of become trapped in that particular area. Okay? So again, T and B lymphocytes are involved in our adaptive immune system. They have different ways of protecting us, which is very important. And there's also another aspect that's quite important. So not only do they act specifically against our particular pathogens, but they have memory. Okay? So when we talk about the immune system and immunity and developing immunity, like we were talking about last time, like chickenpox, the immune system and your immunity develops through time. So you get better and better at defending against these particular agents. And when your immune system gets sensitized to them and gets active, it will then protect you against these pathogens in the future. And so the way that they show memory in this video is pretty funny. Yeah. So you can see that, and it's like your cells become old men there, and they can actually remember what they're exposed to in the past, right? But one other aspect about this, which is very important, different from like our external non-specific defenses or whatever, the adaptive defenses, the T and B cells, can be anywhere in the body. So it doesn't matter where the infection is, we should be able to get these defenses to that particular site. So these are systemic as well. So that's going to be important because we want to make sure that we can protect ourselves wherever this infection is coming from. So this section right here just reminds us of antigens. Now we've been talking about the antigens as these protein markers on the surface of cells, because that our cells will have these antigens that identify them as us, but then the foreign cells will also have them. And so, in essence, what your cells do, your T and B cells and your phagocytes and stuff like that, they have to go and try each of the cells and then say, oh, okay, no, you're on my team, you're okay, you're okay, you're okay. And then, if they find one that is recognized as a foreign antigen and a foreign pathogen, then they'll attack it. And I always like this part of the video, because this is how they're showing how a T cell, for instance, is going to identify a particular pathogen. So he's going along and he's feeling the noses of these guys. Every time he does, he goes, See, and this guy right here, his nose is a little bit bigger, a little bit different, and so that allowed him to identify that particular guy as an agent or whatever. But, again, unlike the soldier with the big nose there, this is like a pathogen like we see here. And all of those little kind of colored markers that you see there, those are the antigens, or the antigenic determinants. And so an individual bacteria can have many, many different types of antigenic determinants or proteins on its surface that it can be identified by. Just like our cells can also have different types of antigens on them. Okay? So these are the things that your antibodies, that your cells are looking to match up with to identify this particular thing as a foreign agent and then be able to try to get rid of it. Okay? So say, for instance, these proteins right here are the antigenic determinants or the antigens that we would be using to identify this pathogen. So what we might have is a floating antibody that would come around, and again, if it has a shape that would fit this antigen, then it would be able to link up with it. And we said that the antibodies are going to be made from our B lymphocytes or B cells. Now when a B cell actually becomes activated, when it becomes awakened because of the presence of a particular pathogen, what happens is it gets a new name and they call it a plasma cell. We'll talk about that when we get into the lecture. But this represents an antibody that would be produced by an activated B cell or a plasma cell. So this antibody would be floating around in the plasma, and again, it may come into contact with this particular pathogen, and if it has the right shape, like that, it would then bind with it. Okay? Which is going to be pretty important in terms of identifying that particular pathogen and then initiating an immune response. So this little figure right here just shows us, some of the things that we find floating around in the blood. We can see the cells, like the white blood cells, the red blood cells, and then you can see some of those antibodies floating around as well. The antibodies give us a type of protection. It's one of our examples of adaptive immune system, our specific immune system, but it's also sometimes called humoral immunity. And the reason it's called humoral immunity is we've seen that humor word before, right? Humor means fluid. And those antibodies are floating around in your fluids, like in the blood. And so that's why they call it humoral immunity. Cellular immunity, the other red term you see it there, comes from the T cells instead, because we said that the T lymphocytes, or T cells, have to go up to the cell and make contact with it and then go fight it hand to hand. So our two types of specific immunity, humoral immunity is the same as the antibody-mediated immunity that involves the B cells, and then the cellular immunity is going to be that which is coming from our T cells or T lymphocytes instead. And the good thing about this website, not only does it have, kind of good animations and things like that, but it has these little checkpoints along the way as well, so you can kind of see how you're doing with the information that they're presenting to you. So for instance, this one says, under what circumstances do you think T cells would attack your own body? So remember we said that not only is our immune system going to attack pathogens, but it would attack like cancer cells as well. And cancer cells, like we mentioned, are cells of our own body. So that one would count. This one says a cell that's been invaded by a virus. So that means, again, it's our own cell, but it's been invaded or hijacked by a virus. So on the outside, it still looks like one of our cells. So that would be something that our immune system would need to be trying to get rid of. Now, bacteria that invaded the extracellular fluid. Now, in that case, right, the question said cells of our own body. A bacterium is a foreign pathogen. We can still identify it, but this is not a case where we would be attacking cells of our own body. And the last one says a cell has been transplanted from another individual. And so in that case, in essence, with a cell that's been transplanted from another individual, that has to do with, like we said, all the different antigens, and if they're similar enough or different enough to our tissues. So if you're getting some transplanted cells, they have to be similar enough to our tissues for you to be able to keep them and not reject them. The rejection that you hear about people like they had a kidney donated or something like that, the rejection comes from the immune system of the recipient. And those cells of that organ may have been pretty similar, but maybe not similar enough. So the immune system cells have identified and started to attack it and try to get rid of it. So most people that actually receive an organ or something like that, not only do they need to be a very specific match in terms of the tissue types, but also that person who receives a donated organ oftentimes will need to be on immune system compromising drugs for the rest of their life. It basically tones down their immune system response so that they don't reject that organ. Now obviously that makes them a little bit more susceptible to things like colds and other types of diseases and stuff like that. But if you're dying and you don't have a kidney or something like that, you'd rather, be getting sick more often and stuff be alive to kind of endure it. So, okay. So anyway, like I said, this was just the first immune system overview of the website. There are other sections as well, so you can see it goes through innate defenses, it goes through comparing B and T lymphocytes, it goes through specifically humoral immunity, again having to do with the B lymphocytes and the antibodies, and then cellular immunity. Okay? So you guys can find that at any time on the web. Like you saw, all you do is do a search for interactive physiology and immune. And it's a good way of reviewing some of the content like we were talking about today. Okay, so let me get rid of that. We'll go back to here. Okay, so now my second persona has disappeared from the site. Okay. So we kind of made it work there. Took a little gear reading, so I can show that to you. But again, I think that the website's pretty good. It makes better honking sound than I do. So if you want to see that for real, you can go back and watch that one. Alright. So where we left off last time is we were going through those 3 lines of defense. And again, like I said, that's one of the, I find, the easiest ways to organize my thoughts about the immune system. Keep thinking those 3 lines of defense. First one is exterior and non-specific, then interior and specific, and then, interior and non-specific, and then the third one is going to be interior and specific. So where we thought last time is right at our second line of defense. So we get done external, non-specific, now we're going to do internal. So, at that point, we're going to have various types of non-specific defenses that can try to get rid of that infectious agent. So, for instance, we have these chemicals that are called interferons. And interferons are targeting viruses. Now, again, when we say it's non-specific, you'll find that some of these defenses do work better on viruses or bacteria or something like that. But it doesn't matter exactly what virus, what strain of bacteria or something like that. That is when we're talking about the specific defenses like they're being teased up. So in this case, the interferons are chemicals that are secreted by cells that have been infected with a virus, and it's alerting the cells in the local area that there's a virus in that area and they need to protect themselves. And in essence, those cells in the local area will then produce these antiviral enzymes, and that will protect them from getting infected by the virus as well. The cell that's already infected is gone, okay? But by putting up this alert, by releasing these interferons, it can help to decrease the spread of the virus to new cells, okay? So that is an example of a second line defense, internal, non-specific. These molecules are called interferons. Another example of an internal defense that is non-specific is fever. And a fever comes about from the secretion of chemicals that are actually called pyrogens. And so pyrogens, P-Y-R-O-G-E-N-S, right? Gen is like to generate, to create, and then pyro, get what pyro means? Pyromaniac. Yeah, so pyro means fire. So these chemicals that are secreted basically generate an internal fire. So they will cause a fever. And so the fever is helping to decrease or the condition for bacterial growth. It's basically making a hostile internal condition for the bacteria. And there's a few things that happen that make it kind of worse for the bacteria. Number one, during a fever, the iron in your body is sequestered inside the cell, and iron is one of the critical nutrients that's needed by bacteria in order for them to reproduce. And so if you take away the substances that they need in order to reproduce, then that's going to slow down the spread of this disease from the bacteria. Also, when things are warm inside, we've added energy into our body, right? So our heart's beating faster, and everything's a little bit warmer. The molecules that are inside our food and stuff like that tend to move a little bit more. And so things, even like cells, our phagocytic cells, tend to move a little bit quicker and attack a little bit more vigorously in order to get rid of these bacteria as well. Okay? So hydrogens are molecules that are secreted internally that generate fever. Fever is an example, another example of our internal non-specific defense. Inflammation. So again, we said you have your skin or something like that, and bacteria are getting in, usually it's swelling on the side of that cup, and that's what inflammation is. And that's an interesting example of how we can, in the body, change blood flow to particular areas. We talked about that before in cardiovascular system, how we can vasoconstrict and vasodilate different blood vessels, which will allow blood to go here or go there or whatever. You can certainly see that in particular areas like this, like when you have a cut, you're going to localize increased blood flow at that cut. And maybe an inch away, it's a little bit lower than what it might normally be. So inflammation, though, or pathogen that's getting in there is going to be basically allowing our different bodily defenses, our white blood cells, to get access to that area that much faster. We want to make sure that if we're being invaded by bacteria there, we can get our defenses there and start battling them before they start spreading too far. Another interesting aspect about inflammation is, in fact, fibroblasts, which are cells that produce fibers, like connective tissue fibers. Fibroblasts will actually start secreting fibers to kind of wall off the area as well. It kind of seals off the area so that hopefully the bacteria can contain within that little infected area as well. Okay, so inflammation is another example of our second line of defense that is internal and non-specific. Another one is phagocytosis. So when we talk about neutrophils, when we talk about monocytes, etc., they are looking to eat up things that are foreign. Okay? So they do have to identify to make sure it's not one of our own cells, our own healthy cells, but other than that, it's just so we can get rid of these pathogens. And so it's very interesting actually with the neutrophils and monocytes and things like that. We saw them as a component of our blood. So when we were looking at the blood, we said that they're red blood cells, because they're 5 types of white blood cells you might see in a sample, and then there were the thrombocytes or the platelets. Now, as you can imagine, if you have an infection, in many cases, it's not going to be directly inside of the blood vessel, right? It's going to be in your skin, or it's going to be in the wall of a particular organ, or something like that, right? So, in most cases, so these cells actually be effective, they have to be able to get to that site of infection. And so, our neutrophils and our monocytes can actually leave the cardiovascular system. So the way that they do that is like the capillaries or the venules and the very small blood vessels. What they will do is they will actually squeeze out. If they're coming to the site of infection, usually there's some chemicals that are being released at that site of infection. And those chemicals will draw in some immunologic defenses. It's kind of an alert, if you will. Kind of like you go into the house and you smell somebody baking cookies or something like that. You can follow that chemical path and find out where the cookies are, right? Now, in this case, we're talking about an infection or something like that. So the chemicals are released by the infected cells, etc. And it brings in things like these phagocytes. And what they do is they'll be in the blood vessel. They can actually attach to the wall of the blood vessel rather than just kind of blowing by. And then they can squeeze out between the epithelial cell lining the blood vessel and start moving to the site of infection. And they move with what's called amoeboid movement. So an amoeba is a single cell organism that we sometimes find in ponds and things like that. And it moves kind of like a snail moves. So it kind of extends out a part of itself, and then it kind of pulls itself along, and then it extends out what's called pseudopod, false foot, and then it pulls itself along. And so there are different types of white blood cells, your phagocytes can do that same thing. So it's interesting to think that these individual cells can move on their own. We always think about ourselves working together with tissues and organs and stuff like that. But these cells in your immune system are kind of little compact defenses that have to go and get there on their own. And so that's diabetes is this process of them getting to the site of infection. Okay, so that's what we just went through then were different examples of second line of defense, internal but non-specific. Okay? So any questions about that? Seem okay? I know it. You'll let me know. Okay. Alright. So now we're going to third line of defense. Now hopefully you guys at least know the cells that are going to get involved in the third line of defense, the specific immunity that we have internal. So two different cells, what do they call them? So this old man cells that we saw right there. T cells and B cells. So the lymphocytes are the main cells of our specific defenses or our immunity. Okay? So we have to talk about how the T cells and then the B cells do their job. Now, like we mentioned, it's going to be very important for all B cells to recognize the different antigens. Our self-antigens so that we know what cells to protect, and the foreign antigens so we know what cells to attack. Now, sometimes there's a fine line in between, okay? If a virus has infected one of our cells, then it's still one of our cells, it's going to have self-antigens on it. But those self-antigens actually get a little bit changed with the viral proteins that are inside of it. And so even those self-antigens will look a little bit different. And enough for our immune system to recognize it and attack our own cells. Because now our own cells look a little bit off. In a way, viruses that affect our cells, cancer cells, they start to, they're our cells, they're not looking right. It's a little bit like they turn into zombies or something like that, right? So with a zombie, right, it looks like a robber from far away, no problem, but then as they get closer, it doesn't look exactly right. Something's off, right? Another robber. And so anything in terms of our cells, so if they become cancerous, if they get virus infected, then they do have cell antigen, but that cell antigen also will go off. And our different defenses will attack those as well. So that's kind of the exception to the role between those two states of self or foreign. Okay? But the antigens are the way that we're going to identify these cells that we need to get rid of. Okay? So we know that there are two cells involved here, the T cells and the B cells. And we said that the T lymphocytes of the T cells are actually going to go through their maturity and kind of boot camp in the environment, while the B cells are going to be created and go through their maturity stages in the bone. Okay? Now, about 70-80% of the lymphocytes that are originally created in the red bone marrow become T lymphocytes and end up getting trained and residing within the thymus and then finally in the different lymph nodes. And then the remainder of them are B lymphocytes. But they both have very specific roles in our adaptive immune system. Okay? And they both will ultimately end up residing in different lymphatic organs, like the spleen and like the lymph nodes and things like that. Okay? So this figure does a good job of showing us some of those differences, so that both the T cells and the B cells can originate in red bone marrow, but in essence, the T cell will go on and mature in the thymus gland. The B cell won't enter circulation until it's fully mature coming out of the red bone marrow. And then finally, both of those cells can reside in things like the lymph nodes, where they can help the defense in certain ways, in their own certain ways. Because as we get into suggesting, B cells and T cells are going to do it slightly differently. Okay. So, and then the general description, we said that the T cells give us a cell-mediated immunity, right? So they are going to be attacking and fighting with these foreign pathogens like bacteria, etc. And they have to have direct cell-cell contact. Okay? And so what they're going to do is they're going to attach to this foreign cell and they're going to try to kill it off in some particular way. Now we'll also find out, much like our other types of immune system responses or bodily defenses, that oftentimes our different cells that are involved with defense will help to recruit other defenses to come at the site of an infection. So T cells also secrete these chemicals that are called cytokines that actually enhance the B cell response and help the B cells or the B lymphocytes to produce their particular defensive function, which is what we were talking about before in terms of producing antibodies. So T cells also can help the B cells do their job as well. So take a look here at this figure, and this figure is from a different textbook. I think this is a good job of showing us exactly how T cells are going to do its role in terms of defending us. So here, we see here is an activated, what's called cytotoxic T cell, right? Cytotoxic, we put that word there, right? Cyto means cell, toxic means poison. So cytotoxic T cells are going to be our infantry doing hand-to-hand combat. You can see how it's bound to this infected cell. Okay? So you can see it right here. And so, this might be, let's say, a virus-infected cell. And so the cytotoxic T cell can identify that kind of mutated or just kind of odd cell antigen that's on the surface. And you see how it's bound with it? Like that. And then what it's going to do is once it has identified it and it's bound with that infected cell, it's going to create different types of chemicals, like you see here and you see here. And these chemicals oftentimes will basically cause holes in the membrane of that cell, and it will degrade the cell, almost like a digestive enzyme, and basically eat away that cell, and cause it to die off. And when it dies off, then we have like more radioactive or neutrophils and peroxides that will combine and produce, and you get some of those different parts in the cellular debris. Okay? But at least you can see in the diagram how a cytotoxic T cell can bind that infected cell, and like I say, bring down those different chemicals on it in order to kill it off. Okay? So now B cells are also going to defend us because they are going to do so in a slightly different way. Because today, when they become activated, they're going to turn into what are called plasma cells. They give it this kind of graduated name, what they call plasma cells, and then they secrete antibodies, something that's not for we're talking about things that we can find in blood. So these are also known as immunoglobulins. That was one of our categories of plasma proteins that we learned about before. We learned fibrinogen and albumin, and then there were these immunoglobulins or globulins. These are the antibodies that are floating around. So B cells, when they produce their response, because that response is called the humoral immune response, because those antibodies are floating around in the humor, in the fluids, primarily blood. Okay? And those antibodies, in some way, are going to help defend us. And we already mentioned one other way, and that is they act like molecular antibodies. So they find up a bunch of cells that they can touch with, and they hold them in place so they can't spread out until the local area phagocytes can come in and take care of. Okay? Okay. So here's just a little bit more detail about each of those two sides. Number one, T cells are cell-mediated immunity, and number two are T cells in our humoral-mediated or antibody-mediated immunity. Now, we just got mentioning the cytotoxic T cell, the one that binds the cell, bringing down chemicals on them, poison on them, and kill them off. But in fact, there are two other categories of T cells that exist. One of them are called helper T cells, and this is that other function that we mentioned a little bit earlier. The fact that there's a certain set of T cells that will release chemicals that are beneficial chemicals that actually stimulate B cells to increase their production of antibodies and things like that. So helper T cells don't go out and attack the pathogen. What they do is they cut the B cell response, and that's the way they get their name. Okay, so that's another category of T cells, helper T cells, cytotoxic T cells, and the last group are the memory T cells. So in the animation we saw, our T cells that had a long white ears, etc. Okay, in essence, when you get infected with something, it's a very interesting and unique process, right? There's millions and millions of different things that you can be infected with over your lifetime. We said like viruses, as they reproduce and mutate through time. The same flu virus that they got infected with last year, in the years since, it's possible that if you get it enough, that even though you successfully, got through that flu last year, you should have memory of it, develop it, and get rid of it this year. It could be that flu virus mutated enough that it's now recognizable by those same cells. So what happens is, you've got B cells and T cells that have these receptors on the surface, and each receptor is slightly different. So this T cell might have receptors shaped like a triangle, this T cell might have receptors that are shaped like circles, and this T cell might have receptors that are shaped like squares or something like that, right? But stretch that out to almost the millions. Okay? We've got all these different T cells and B cells that are slightly different from one another in terms of their receptors. And that gives them the ability, the chance, that when you become infected with a pathogen, there's going to be one of those, all those T cells and B cells that are going to match exactly the antigen on that pathogen. Okay? And then that particular T cell or B cell is going to be the one to take care of that pathogen when you get infected with it. Okay? So it's almost like a dance or something like that, right? So it's like a huge high school dance where it's like all these guys are lined up against the wall, the girls up, and they go, no. Okay, we're matching somehow, so we're going to go dance, right? So think of that in terms of actually like millions of different types of T cells and B cells. When you get infected with a cold or flu or any type of pathogen, there's going to be one of those that's actually going to match up that pathogen. And when that happens, that particular cell is going to be activated. But hey, that one cell is going to be able to defend us like one of those soldiers to fight off all of these invaders, right? Well, what happens at that point is that one has the right receptors, right? And that pathogen, we need a whole bunch of that particular type of T cell or B cell. So what happens is a ton of mitosis, like we talked about before, we need that cell to replicate crazy, out of control, but in control by a lot, so that we have a lot of clones of that particular cell to fight off that pathogen and infect with. In a way, that's kind of like, Star Wars, right? You got Star Wars, the original ones, the ones that later became 4, 5, 6, and then 1, 2, 3, and all 4. But anyway, there were basically a clone army that was generated, right? So this is generated out what Django said or something like that, like go with the dad. I don't know, okay, it's not that much. But anyway, if you were watching that movie again, right? There was that one planet, that one bounty hunter, and then Django said. And then he was, the very big guy, and they have this whole clone army of that one guy, because he had the characteristics to be a good defender, right? So you have a whole army, very easy to do, very quick, and now have a whole army that's very effective at defending, okay? That's what goes on in terms of eating the B cell. So I have one B cell, one T cell gets activated, and then we need clonal replication of that particular one, so we have an army of clones that defend us. When it's a T cell, they're going to have fine, because they're going to on that. If it's a B cell, it's going to be bonded to that one particular clone of B cell. It's going to be pumping out antibodies to defend against that. Okay? Now, the memory cells that are made on that particular clone, when we're making those clones, what happens is the point of those continue to battle at that time, but certain subsets of those, we're actually going to hold back. And if we hold back those memory cells, and we keep them out of the battle, those like in the battle, all those cells are going to die. Okay? If everybody dies in that battle, then it's the whole phrase of those that don't remember history or repeat, right? So if you want to cells that are surviving the battle, there's nothing to remember what that particular pathogen was. So you can take a bunch of memory cells, memory T cells, B cells, that we sequester to hold back, and those stay in your circulation to protect you in case you get infected with that pathogen again in the future. And that's why you get those in the future. You've got those cells already there, they identify what it is, they quickly clone themselves, and take care of it very quickly. Okay, so the point here is that with our cellular immune response, it comes from our T cells, and we have 3 different types. Cytotoxic T cells, the hand-combat warriors, the helper T cells, about the B cells, to get their immune response going, and then the memory T cells are the ones that are going to stay around in our body, not fight the battle right then, but be there for the future in case you get infected with it in the future. Okay. Our B cells, like you said, give our normal immune response. So when they become activated, they turn into plasma cell. And as a plasma cell, we need a ton of those particular plasma cells, those clones, and as we make a bunch of those, then they're going to start pumping out these antibodies that will protect us. Okay? Now, just like B cells, we need to, for that particular clone, get some memory B cells that they're going to hold on to for long-lasting protection too. So technically, there's 2 different types of B cells, right? Those that are in the battle producing antibodies, called plasma cells, and those that are going to be kind of stored or later used called memory cells. Alright, so this picture is again taken from different textbooks, but I think it does a good job of showing you some of the things that I'm talking about. So let's take a look at this very top panel right here. So here, for instance, there are 4 different types of B cell clones, okay? And look at the receptor on their surface, right? The receptor on the surface is slightly different in terms of the shape. Here's a particular pathogen that comes to us. And here's the data, right? This brown pathogen here doesn't fit this one, doesn't fit this one, doesn't fit this one, but this one fits just right. Okay? Like a lot of 3 bears. Like a lot of million bears. Okay? So this is the particular clone we're going to need. This is a clone. This is a B cell that's going to be effective against that particular pathogen. So what we do is we start making a bunch of these these particular B cells with that receptor. Now, activated B cells are called plasma cells. And if you look at them, they become much bigger, right? They're almost like they become a rebel hole, right? They get angry, they get really big. One reason they get really big is they get a ton more about the plasma reticulum inside of it. And what is that plasma reticulum do? It's way back there. Let's weeks ago. So as one of our organelles, the main job is to make proteins. Those protein making factors. Antibodies, like we see here, are proteins. So these cells can crank out proteins. They make a lot of plasma reticulum. So here's a whole array of plasma cells. They're cranking out the antibodies here. They're going to be moving into the fluid, and they can bind out those antigens and work through that pathogen. Here on the right side, you can remember now, at the right side, we're going to hold on to those for later use in case you get affected by that pathogen again. Okay. So this is your right here comes your book. It kind of describes some of the things that the T cells, B cells do, and how you remember kind of the differences that you're talking about. This here kind of shows all together what's going on in terms of our T cells, B cells, right? So they both originate in the bone at the very beginning. Because the T cells are going to mature in thymus. B cells are actually going to mature in maturation of bone. We said that the T cells come into a couple different types. They become cytotoxic T cells, like we see here. They go out and combat and bind to our infected cells. And there's also helper T cells. And helper T cells will also activate B cells. And the B cells will only become plasma cells. And plasma cells will found antibodies to our different bodily fluids. Okay? Now, there's a lot of different types of antibodies. You won't have to worry about the different types like animals here. But it just gives you an idea of the diversity of the antibodies and kind of where you can find them. So you see exocrine secretions like sweat glands here, something like that, in the plasma of the blood. Also in, you can talk about even in the secretions from the surfaces of lots of different organs. So one of the things that we have to think about is this is a protein, and it's floating around in the fluid. Well, how does it work to protect us? It's a little easier to think about cytotoxic T cell because it's a living cell, and it can move, and it has receptors that can bind another cell and kind of check things, right? But these are molecules. So how is it that a molecule is going to defend against that pathogen? Well, one of the main things that we talked about was that contamination when combined with the surface and other particular bacteria and something like that. And so that's very good function for the different antibodies. But there's one other thing that they do as well. One thing called oxidation. And oxidation, when they hit the surface of a bacteria or something like that, it actually makes it a little bit easier for a neutrophil or a macrophage to come up and grab onto it. It now has all these key antibodies against the surface. So now that phagocyte can grab onto it a little bit easier. And so also chemocatalysis. So chemocatalysis is when we have chemicals that we're working to track other events like we were talking about before, like smell cookies. And so the antibodies in a little area can work to track other types of cells, like phagocytes and things like that. It's also possible for our different antibodies when they attach to the surface of a pathogen. Here, right here. They can attach to the surface and they can actually attach to each other. In this case, we're working with a membrane complex. You know here? Each one of the little bars right here represent a protein antibody. And so if you want them in the area, they can actually form a hole or a pore in the side of the membrane itself. And if we form a hole in it, it's like basically a hole in the tire, right? Take a screwdriver, put it in a tire, it just deflates. same thing comes to the cell. If you get one big hole inside the membrane cell, then all the interior is going to spew out and come down. Okay? So that's another way that the antibodies naturally affect our pathogen. And that's what the activation component. This is the complementary proteins are some of the things we see here. Some of them are antibodies, but they start a chemical reaction and form these membrane complexes. And these other proteins are called complementary proteins. Right there, saying double anti-membrane like that. They're basically before the membrane itself. So there's a number of ways antibodies, even though they're just molecules, can actually help kill off particular bacteria or something like that. Okay. So this slide right here, you don't have to do, I would say, you wouldn't have to do anything like reduce graph or anything like that. But what it's showing you is that this on the x-axis shows time in days, and on the y-axis shows antibody titer. And that's how many antibodies are in a particular fluid. Okay? Now what happens is, when we're searching on something, we're seeing the first exposure data right there. And so primary response is you'll see this time when your different T cells and B cells have to go attach to the DNA, which is the right one. And once that's unlighted, if B cells are coming out the antibodies are going to be the right one, you'll get better, and then you'll heal from that infection. And that's what we see here, where we see antibodies level up, and now you'll heal from that. That takes a number of days for that little white spot to occur, the antibodies go up, and then they'll go around and you get better. Okay? Now, if you look at that second exposure, we're seeing that pathogen. So you've been exposed, right? So something in your face, you got sick, you got better, and then somehow, right? Somebody gets into your face, that same pathogen. Okay? On the second exposure, no common factor, and how more it response you get in terms of the number of antibodies produced. And that's because the memory cells have been there, and they say, oh, I know this, just add this, I totally know how to get rid of this, we need a bunch of meat, they're reproducing hormonal clones, printing out antibodies, and you get over it a lot faster than you maybe your first time, how intense response care. So the secondary response, secondary exposure comes from memory cells, not having to do that whole, kind of testing out and things like that. So that's just the benefit of our memory cells. Okay. So the defenses that we have are very active type of studies. We talk about different cells involved, different molecules, etc. Different time upon our exposure to different disease-causing agents, makes us better able to defend ourselves against agents in the future. But different types of ways we can classify this immunity or bodily protection. Now, most of what we've been talking about is first where the naturally acquired active immunity. What that means is, by somebody using their face, okay, you are exposed to pathogen, your body has to go through a process of fighting T cell, and then fighting it off, and you have to have it bring afterwards, okay? So that's a natural way to generate our immunity. So that naturally acquired active immunity active because your whole body cells have to be active in the response, okay? Now, what we find is there are other types of immunity as well. Now another one called artificially acquired active immunity as well. So artificially acquired active immunity is talking about like vaccines. So vaccines, the way that vaccines work is that vaccines, you have either dead viruses or very, very weak viruses that are put into a syringe. And they're purposely injected or exposed into your body. And so just like some ACE or something like that, there's enough of those little protein markers or your cells, your defense cells to recognize. Okay? So that generates an immune response in your body. So different T cells will become active, and then have those memory cells protect you against that pathogen in the future. But the benefit of vaccine is that because it's weak or dead viruses, you don't get full-blown disease. You don't have to go through the whole thing with chickenpox. You can actually now get a chickenpox vaccine, and it still awakens and activates your immune system against the chickenpox virus without having to go through having the disease. And so that's why at the beginning of people's lives, there's a lot of vaccination, right? So there's like measles, mumps, rubella, and all that type of thing. So one time people go through these diseases, and a lot of people die because they're pretty severe, and their immune system couldn't handle it. And so now they develop vaccines that they can expose your body to it without giving you the full-blown disease. It gets your cells up and allergic to it, and now you're protected against it. And usually those things are lifelong. Now in some cases where you lose stuff like that, right? Tetanus. Tetanus are supposed to get boosters every 10 years or so. Of course, it's really hard to remember when that last one, etc. But most of these things, you get like a kid, and you're protected for the rest of your life. But this is all artificially acquired immunity. Right? So you artificially acquired this with vaccination, but with your own immune system actively generating a memory cell protecting you actively in the future. Okay. Two other types of ways to acquire immunity. The third way is called artificially acquired passive immunity. And in this case, this is where you can get injected with antibodies. So say you're going to surgery or something like that. You can imagine that your outer defense system is going to be very compromised, right? They're going to try to have sterile conditions, etc. You're going to have your immune organs exposed to the outside environment. So you're not trying to do whatever you can to ward off, attack at that point. And so they may inject you with antibodies and antibodies. And those antibodies can do the same thing. Like fighting more cells, they like bacteria, they may etc. So artificial acquired is called passive immunity. You didn't produce those antibodies. There's no B cell activation to bring those out or anything. So it's very short-lived response or short-lived protection. Maybe only last a week or two while you're recovering and stuff like that. Okay? But anyway, getting some protection is short term. That's artificially acquired passive immunity. The last one called naturally acquired passive immunity. And this is where antibodies are half, either from mother to kid or from mother to baby. So this is where antibodies happen to the placenta, and those antibodies that are produced by the mother are then passed to the fetus and help the fetus, or we talk about breastfeeding. These antibodies can be passed to a baby in that way. Now remember, the baby is not making these antibodies, so it's all passive immunity. Passive immunity, doesn't have to do anything. So the baby can benefit from it, but it's not actively producing. So it's short term. But it's getting the extra layers, especially when you're in those almost defense states like that. Okay. The last thing, a lot of things that happens to the allergies. So allergies, right? So a lot of times you have allergies, you have the same thing like response, right? You have congestion, coughing, water eyes, stuff like that. How is allergen different from a pathogen? Well, an allergen is going to be something that sets off your bodily defenses, but it's not a disease-causing agent. It's not something that's actually going to replicate inside of you, trying to make more themselves, living, etc. Okay? So allergen is going to be things we mentioned before, like dust, or pollen, or pet dander, or peanut these days. There's a lot of other things that have been related to allergies to people. And so in this way, your immune system is reacting, right? It's reacting to that particular substance, and this is a disease-causing agent. And so you get the same type of response, like inflammation like swelling, like you could so you can track whatever that allergen is, so it doesn't get precise, etc. Some people have green reaction, right? So they'll have bronchitis. which I bring this to my left and on the top, but I saw it works well for the example right now, right? So for people that have bronchitis, the deal is that allergen is so very reactive to their immune system. Their bronchioles, their air tube will actually constrict as muscle right? They'll constrict in order to try to not get more allergen inside of our lungs. Now, of course, the problem is, right? You're not getting allergen, then you're not getting oxygen and carbon dioxide exchange you do as well. So things like these that have steroid hormones in them that will cause the bronchioles to dilate again. The chemical stimulants will get those bronchioles dilate. So we've got certain reactions or allergens, things like antihistamines, like we talked about before, are good things to do because you can tone down our body's response to this overreaction to something it shouldn't. Now, if you actually have a cold, a flu, or something like that, what I try to do is I try not to take anything. Because my own defenses that we've been talking about are trying to do combat, right? And you can take anti-inflammatories, fever reducers, and antihistamines, stuff like that. All these anti-things I'm talking about are anti-against your natural defenses, the way they're trying to get cells outside of infection and increase blood flow to it, and really get blood in there and things like that. And so what I'm doing is actually prolonging the time you're sick because you're taking down your defense, right? Fever that makes everything more active. The phagocytes are trying to heat up better. Well, you take ibuprofen or like Tylenol to reduce fever, well, you feel better, but now, because the bacteria are going to be able to reproduce a little bit, etc. Hard to say. Now, obviously, you have to do class, teach or something like that, and maybe take stuff so you can get through the day. But what I try to do is, if it's not too painful or bad or something like that, and I'm not sick, I try to let those things happen, because letting our body do what it's supposed to be. Okay. So anyway, allergic reaction is one of our last topics. The other thing you might hear about is things like autoimmune diseases, etc. We already talked about transplants, things like that. So autoimmune diseases is where your tissue or your immune system have lost the ability to identify friend or foe, right? To identify self from foreign. And so you'll have some of your bodily defenses that will actually attack your own tissue as if they're foreign. So there's a number of different types of autoimmune disease. So for instance, different types of arthritis, rheumatoid arthritis, where the muscles get really swollen like that. That's actually an autoimmune disease where it's attacking tissues of the joints, etc. So there's a number of different diseases like that. So in any case, when you hear about autoimmune disease, that's what's going on. The immune system has lost its ability to tell the difference between what it should attack and what it should attack.